Good morning, everybody. Welcome back to your YouTube channel, Shri Chaitanya Educational Institutes. Today, in this class of organic chemistry, we'll be talking about tautomerism. As you have already studied about what is geometrical isomerism and what is optical isomerism in the last 2-3 classes. Okay, so today we'll be talking about tautomerism, which is a part of structural isomerism. Tautomerism. It has some other names as well. It is also called as prototropism, or it is also called as catatropism. Okay. Good morning. Good morning, Niharika. Good morning, Mahendra. Good morning, Bhavani. Okay. So today we'll be talking about tautomerism, which is a special type of isomerism, special type of structural isomerism. Why this is so special and different from the other isomerisms is because here actually there is a reaction happening. Okay, there is a shifting of groups happening. Good morning, Mahendra. Good morning. Shifting of groups happening. So what happens in tautomerism versus other isomers? When you have two functional isomers, beta, let's say you have a propanone, you have a propanol. Propanone and propanol, they will exist in different containers. Okay, so two isomers do not exist together, but tautomers always exist together in equilibrium with each other. So actually a reaction is happening. A is converting to B, B is converting to A at equal speed after some time, and it reaches to equilibrium condition. So what are tautomers? Tautomers are special type of isomers which always exist in dynamic equilibrium. Dynamic equilibrium. Good morning, Neeraj. They exist in dynamic equilibrium and they keep converting from one form to another by a shifting of proton from one atom to another atom. Shifting of proton, H plus will shift. That's why the name prototropism. Proto means proton. Tropism means transfer, proton transfer. Catatropism, because all this will happen in the presence of a catalyst. That's why the name catatropism. Okay, tautomerism, prototropism, catatropism all have shifting of proton from one atom to another in presence of a catalyst. And the two tautomers always exist in dynamic equilibrium with each other. Yes, so let us write down tautomerism. Write down two compounds with same molecular formula which exist in dynamic equilibrium with each other. Exist in dynamic equilibrium with each other and are interconverted by proton transfer. Interconverted by proton transfer from one atom to another. One atom to another. Proton transfer from one atom to another in presence of a catalyst. In presence of catalyst. So here the catalyst will either be an acid or a base. So acidic medium or basic medium, any medium can be given. There the tautomerism will occur. in the presence of acid catalyzed or base catalyzed condition. Now, the thing comes, tautomerism can be of different types like dyad system, triad system, but you have to only study about triad system in your syllabus. Okay, triad system we'll study. So we'll only talk about triad, means 1,3 system. Shifting will occur from first atom to third atom. Okay, for our syllabus, all the shiftings are triad shifting. Some of them are pentad also. I'll show you example. One example of dyad also I'll show you. Dyad shifting means 1 to 2, means from first atom to second atom shifting will happen. Triad means 1 to 3. From first atom, proton will shift to the third respective atom. Okay. Very simple condition is there, beta. Direct condition I'll tell you. Condition is very simple. You should have a sp3 carbon directly attached to a sp2 atom, which is double bonded or triple bonded to third atom. This condition is there. Simple condition. Whenever you have such a condition, means a carbon which is sp3, means it should have 4 sigma bonds, directly attached to a sp2 atom, which is double bonded to another atom. This carbon, the sp3 carbon, we'll call it as alpha carbon. This could be present in ketone. You can see here, you can have a ketone like this. You can have a aldehyde like this. This is a aldehyde. You can have this condition in a nitro compound. This is N double bond O, coordinate bond O. You can have the similar condition in different types of compounds. Nitroso also you can take, nitroso. N double bond O, like this. This is a simple condition. Presence of alpha sp3 carbon directly attached to a sp2 atom. This is the condition. Whenever this condition is satisfied and there must be a hydrogen present on this sp3 carbon, we'll call it alpha hydrogen. So what is the condition, beta? Presence of alpha hydrogen on an alpha sp3 carbon, which is directly attached to a sp2 atom. Then tautomerism is possible. What you have to do? Simply say to yourself, you will do one reaction where you will say like this: sigma become pi, pi become minus, minus take H plus. Okay, you will speak like this. Speak like this yourself first, 2-3 times. Say like this: sigma become pi, pi become minus, minus take H plus. Okay, keep speaking like this. Sigma become pi, pi become minus, minus take H plus. Sigma become pi, pi become minus, minus take H plus. So what you have to do is, you have to take the sigma bond of the alpha carbon and hydrogen, make it pi, sigma become pi, sigma move it ahead, become pi. Then this pi become minus, means this pi go to B and it becomes negative charge. Sigma became a pi bond, sigma moved ahead, sigma became pi, pi became minus. This minus goes and takes this H plus, collects the H plus. That's all. Sigma become pi, pi become minus, minus take H plus. So once we do this shifting, see what will happen, everybody. This hydrogen I am just showing it with yellow color or some red color, let's say. Make an equilibrium sign. After this shifting, what will happen? See, this carbon will get 2 sigma bonds here, which are these two, and you'll get a double bond with A. This pi bond have shifted to B, so this become a single bond B. And B has gotten the H. B gets the H. Like this. These are two tautomers. These are the two tautomers. Okay. where the shifting has happened from carbon to oxygen or carbon to B. If carbon was atom number 1, let's say, respectively, B was atom number 3. That's why we call it as triad shift or 1,3 shifting. Proton has shifted from first atom to third atom. Sigma become pi, pi become minus, minus take H plus. Okay, this is how tautomerism is to be done. For a triad system, for a pentad system also I'll show you the example. Okay, so starting with the first example, keto-enol tautomerism. Example number 1, case 1, we call it as keto-enol tautomerism. So this is a keto form, okay, keto form. When you will do tautomerism, you see what will happen. Sigma become pi, pi become minus, minus take H plus. Sigma become pi, pi become minus, high alpha high. Sigma become pi, pi become minus, minus take the H plus. Draw the sign of tautomerism or equilibrium. Let's keep here hydrogens or alkyl, anything you can keep. I am keeping 2 alkyls, RR. So what I am left with is this C double bond C, single bond OH. This proton has shifted. Let me paint it as a green color proton. So what we started with was a ketone or a aldehyde. Ketone or aldehyde, you can call it as keto form. Okay. This became an enol. So this is enol form. So this is called as keto-enol tautomerism. We call it as keto-enol tautomerism. And this is the one which is most important. Any question which will come in NEET will be from keto-enol tautomerism. Niharika, you can ask me. I'll tell you. First thing, look at the condition, Niharika. I'll write the condition as well. Presence of alpha sp3 hydrogen, sp3 carbon and a hydrogen on it. So do I see that there is a sp2 carbon? Yes, sir, there is a sp2 carbon. Just put a star there. sp2 carbon, you call it as star carbon. And the next atom, you call it as alpha. The one present next to the sp2, we'll call it as alpha. Alpha carbon carrying a hydrogen. Yes, sir, it is carrying a hydrogen. Means tautomerism, it will show. What you need to do is sigma become pi, pi become minus, minus take H plus. So this sigma bond became pi bond. Pi became minus, minus took the H plus. So what happened? This H plus went to oxygen. This sigma became pi here. And this pi became pi went up. So I hope there is no confusion. We went from keto to enol. Keto-enol tautomerism. Okay, Niharika? Next one is a nitro group. Let's keep some alkyl groups here if you want, or you can keep hydrogen, not a problem. If 2 hydrogens are there also, there is not a problem. So I started with CH3NO2. You see how the tautomerism will happen. I first saw star atom. This is sp2 atom. We'll call it as star, sp2 atom. The next atom is alpha. This is alpha carbon. Is alpha carbon sp3? Yes, condition is satisfied. Then, does it have a hydrogen? Yes. Then do it. Sigma become pi, pi become minus, minus take the H plus. Tautomerism. What is the other tautomer looking like? CH2, double bond N, OH, coordinate bond O. Okay, beta. This is how it is looking like. Hydrogen I am showing with the green color, the one which is shifting. So as you can see, shifting is always occurring from first atom to third atom. If carbon is first atom, second, third atom, 1-3 shift. It is called as nitro nitro tautomerism. Okay, this is nitro functional group. When a hydrogen is attached to nitro, we call it as nitro, ACY, nitro. So this is nitro nitro tautomerism. Nitro nitro tautomerism. So I am telling you the different cases just so that if a question comes, which of the following can show tautomerism and cannot show tautomerism, we should be able to tell. So condition is simple. A double bond B kind of thing should be there. A double bond B kind of thing should be there next to alpha carbon. Yes. Next is nitroso. This is beta nitroso functional group. Nitroso. Nitroso. Is the condition satisfied? Yes, sir. I have a star atom which is going to be sp2. I have alpha carbon. Alpha carbon carries a hydrogen. So yes, sir. This can also show tautomerism. I'll keep other also hydrogen. Sigma become pi. Pi become minus. Minus take the H plus. So what do I get? I get CH2 double bond N single bond OH. Okay. This type of functional group, carbon double bond NOH, is called as a oxime. Called as a oxime. So nitroso has converted to oxime. So this is called as nitroso oxime. Nitroso oxime tautomerism. Nitroso oxime tautomerism. Like this, many more can be there. Like this, many more can be there. 3 examples I have given you. Only keto-enol tautomerism is the one which can be asked in the exam. Which can be asked in the exam. I hope it is clear. So we'll write the condition. We'll write the condition for keto-enol tautomerism. Write down. Conditions to exhibit keto-enol tautomerism. Conditions to exhibit keto-enol tautomerism. The condition is simple. First one, presence of alpha sp3 carbon. Presence of alpha sp3 carbon. The carbon directly attached to C double bond O must be sp3. Carbon directly attached to C double bond O group must be sp3. So this carbon must be sp3. Should not be sp2, it should not be sp. This must be sp3. Second condition is proton shifting obviously require a proton. So alpha proton must be present. So second condition is presence of at least one. Presence of at least one. There can be 2, 3 also, not a problem. Only one will shift. Presence of, yes, Neeraj, that will come at the end. That will come at the end, intramolecular. You have to wait for that. Presence of at least one alpha hydrogen on alpha carbon. Okay, presence of at least one alpha hydrogen on the carbon. This is the second condition. Here a hydrogen must be present. I just told you this condition already. So this is the one. Okay. So by looking at some molecules, first I will tell you how to predict who can show tautomerism, who can not show tautomerism. And because tautomerism is the dynamic equilibrium, that means you can also come from enol to keto form. Whenever you get an enol can also show tautomerism. You can come back to keto form. For example, if the question is, can this show tautomerism? If they ask you a question like this, can this show tautomerism? Answer is yes. Answer is yes. What is this? It's a enol. Whenever you have a C double bond C, and that C double bond C only is carrying the OH group, that is a enol. So if keto can become enol, then obviously enol can become keto. So answer is yes. And then you can show also. Sigma become pi, pi become minus, minus take the H plus. Exact opposite you do now. Same, sigma become pi, pi become minus, minus take the H plus, but in the opposite direction. See here, this is enol. We know that the hydrogen on the oxygen, this hydrogen will shift. Obviously, this hydrogen will shift now. This is the sigma bond. Just move back now. Sigma become pi, pi become minus, minus take the H plus. So this green or this hydrogen which was here, I'll call it as green hydrogen. This green hydrogen which was here, now it has shifted to this carbon. So what will happen? You see here. Sigma became pi, so this became C double bond O. This pi became minus, so H came here. So we have gone from enol to keto form. We have gone from enol to keto form. Okay. So this is how keto-enol tautomerism can be checked. Now I'll write few molecules. I want those who are in the class to tell me how many of the following or which of the following will show tautomerism, which of the following will not show tautomerism. And some exceptions will come here. Okay. Okay. Which of the following can show or can exhibit tautomerism? And once we will check who will show tautomerism, we'll draw its tautomeric form also. The other tautomer also will draw. Okay. First one. Second one. Third one. Fourth one. Fifth one. Sixth one. Seventh one. Sixth one. This is the seventh one. Eighth one. Ninth one. Okay, so these are the ones we are going to do right now. In this, few cases are there which we need to remember as important ones. And remember how their enol form look like. Okay, if I look at the first one, beta, let's look at the first one, everybody. So first one is a ketone, and on this side there is a alpha carbon, but the problem is alpha carbon does not have hydrogen. Alpha carbon does not have hydrogen. These are methyl groups, na beta. This side, yes, this alpha has a hydrogen. So this alpha carbon's hydrogen can do the shifting. sigma become pi, pi become minus, minus take the H plus. So yes, first one can show. And draw its tautomer also. Tautomer is going to look like this. Tautomer is going to look like this. Keto became enol. Like this we have to check. Second one. In the second one, I have the star carbon. This side alpha carbon is to sp2. So this is to not satisfied. sp2 should not be there. Otherwise, hydrogen can't shift. This is alpha, this is sp3, but there is no hydrogen here. These are to methyl, methyl. So no hydrogen means it cannot show tautomerism. No, it cannot show tautomerism. Okay, first one can show, but second one cannot show. Can the third one show? Yes, sir. This is the star carbon. This is the alpha carbon. Alpha carbon is sp3 and it carries hydrogen. It carries hydrogen. So we can do the shifting. Sigma become pi, pi become minus, minus take the H plus. So yes, it can show tautomerism. So its other tautomer will look like this, which is nothing but phenol. Pi here, pi here. This sigma became pi here. O became OH. This is phenol. See beta, generally keto form is much more stable than enol form. 99% of the time at equilibrium, keto form will be almost like 99% and this will be almost 1% or less than that only. Okay, just the approximate value I'm telling. So in equilibrium, 99% keto form exists. Only around 1% enol form exists most of the times. Most of the times. Okay, so out of 10 cases, in 8 or 9 cases, you will see keto will be more stable. Why? Because C double bond O has more bond energy than C double bond C. So when you ask pi bond, where are you more happy? Pi bond says that I am more happy in C double bond O case and I'm less happy in C double bond C case because keto pi bond is much more stable than an alkene pi bond. Okay, but sometimes, a few times, only 2-3 times, it happens that enol becomes stable. When will that happen? Whenever you get final enol as an aromatic compound. So in this case, phenol is aromatic in nature. It has a benzene ring. Benzene rings are very, very stable rings when you study aromaticity. So aromatic enol, this is like almost 100%. 99.9% will be this, almost 0% will be enol. So yes, there are conditions which can make enol to be very, very stable and keto to be very, very less stable as compared to enol. One of the thing is aromaticity. Whenever enol gets aromatic character, its percentage increases to almost 100%. Exact reversal has happened. So generally it is like this, but whenever the final product is phenol, then enol is becoming aromatic, almost 100% it goes to forward. Okay, so at equilibrium you will find crores and crores molecules of this, but only 1,000 molecule of this. That means this is 99.99%, this is almost 0.01%. Okay, write it down. Then tell me others can show or not. 4th, 5th, 6th. Can the 4th one show? Yes, sir. 4th one can also show. This is the star carbon. This is the alpha carbon. Alpha carbon is sp3. It has hydrogen. So you do the shifting by writing sigma become pi, pi become minus, minus take H plus. I'll do it without it. Okay. You should draw the arrow because you are not having much practice of it. I have practice, so I can directly draw the product. So yes, it can show. Will the next one show? These becomes important compounds, please remember. Beta, these carbons are called as bridgehead carbons, from where a bridge starts. These carbons are called as BHC, bridge head carbon. Bridged head carbons. These are sp3 carbons actually. Okay, these are sp3 carbons. But these carbons can never become planar because from here a bridge is starting. So whenever you take two cycles, something like this, and from the middle you add one more cycle here, like this or like this, then these carbons become bridge head carbons. From here a bridge starts. Bridge means flyover. And we know that a flyover can never be planar. Obviously, flyover has to go out of plane to become a flyover, no? So these are called as bridgehead carbons, and bridgehead carbons can never become planar, means they can never become sp2. They can never become sp2. This is one rule that you should remember. Bridgehead carbons can never become sp2, can never become planar. So this I am writing somewhere. You can also remember. Bridgehead carbon can never become planar or sp2. That means the hydrogen present on bridgehead carbon, can never take part in tautomerism. Why? Because if hydrogen takes part in tautomerism, sigma becomes pi, then BHC, bridgehead carbon, will become alkene. It will become planar, which is not possible. So remember this, alpha hydrogen on bridgehead carbon can never take part in tautomerism, can never show tautomerism. For example, see the next to next. See everybody here. See here. In this compound, this is the star carbon. Next to star, this is alpha, but this alpha is useless for me because this alpha does not have a hydrogen. Okay, useless. Coming to this alpha, this is also alpha carbon. This carbon is also sp3. It has one bond going here, one bond going here, one bond going for CH2, and one hydrogen. So although there is a alpha hydrogen present, alpha hydrogen is present on sp3 carbon only, but the shifting is not possible here, because if I do the shifting, I'll say sigma become pi, pi become minus, minus take the H plus. I'll do like this. Once I do this shifting beta, the final product starts looking like this. Please see here. Final product starts looking like this. This became OH and a pi bond came here like this. And I just told you that if this carbon is sp2, then how it can go out of plane? So this is not possible. This is not possible. Don't do this. Bridgehead carbon can never become sp2. So answer is no. It cannot show tautomerism. Please remember, as an exceptional case, although sometime alpha hydrogen is present on sp3 carbon, but if that sp3 carbon is a bridge head, from there a bridge is starting, then there is no possibility of tautomerism. Same way here, this is bridge head, so it's hydrogen, so I cannot choose. This hydrogen is useless. But this is also alpha carbon. It has one methyl, that means one hydrogen is present here. So this hydrogen can show. Yes, answer is yes, it can show. Sigma become pi, pi become minus, minus take the H plus. So yes, in this one, tautomerism is possible, and we get the enol form, which looks like this. Okay, so like this we can check for the tautomerism. In all these cases, your enol form will be much less stable. Okay, 99% keto, 1-2% enol. Okay. So I just told you keto forms are always more stable. Only a very few times enol form become more stable. Okay. Let's take the next example now. Let's take the next example now. This is another important example. As an exception, you should remember, this is an example of pentard system. Means 1-5 shifting. 1-5 shifting. Remember it, beta. Whenever your alpha carbon is sp2, don't lose hope. Don't lose hope. Whenever alpha carbon is sp2, don't lose hope. Check gamma carbon. Check which carbon? Gamma. Alpha, beta, gamma. Alpha is sp2. So beta obviously will be sp2 because if a pi bond starts from alpha, pi bond will go till beta. So don't lose hope. If alpha is sp2, check gamma. If gamma carbon satisfies the condition, then also tautomerism can happen. Okay, this is called as pentard system, 1-5 shifting. See here. So this is the star carbon. This is alpha, but alpha is sp2. This side also alpha is sp2. So I should not lose hope. I should check gamma. Beta, gamma. Is gamma sp3? Yes, sir. Does gamma carry hydrogen? Yes, sir. So either shifting can occur from alpha carbon, or if alpha carbon is sp2, then only. Don't think if alpha carbon is sp3 and no hydrogen, leave it. No hope. If alpha carbon is sp2, then don't lose hope. Go to gamma carbon. If gamma carbon is sp3 and carry a hydrogen, then yes, tautomerism can occur. Tautomerism can occur. So now you do the shifting. Same, sigma become pi, just one extra step will come here. Sigma become pi, pi become pi, pi become minus, then minus takes the H plus. One extra step will come. Sigma become pi, pi become pi, pi become minus, minus take the H plus. Like a resonance, it will automatically go. Sigma become pi, pi become pi, pi become minus, minus take the H plus. So in a pentard system, this is how the equilibrium will come. So you can see here, this became a pi bond here. This pi bond shifted here, and this pi became minus, O took the H. This also became phenol. So you can see here that this person also shows tautomerism, and the one I wrote on the third position, that also shows tautomerism, this one. Although they were looking different, but their enol form is same. Okay, they were looking different. This was 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So 2, 4 diene, and this is 2, 5 diene. But there 1, 2, 3, 4, 5, 2, 5 diene, but their enol form looks the same only. This is called as 1-5 shifting. Although it is very rare, remember this one example where this can also show isomerism. Okay, so two exceptions we have studied just now. One exception was bridgehead alpha carbons cannot show tautomerism, and second one is pentard shift is possible when alpha is sp2. Then go and check gamma. Go and check gamma. Can next one show? Answer is yes, sir, it can show. Okay, I'm not drawing it, but you can just see here. This is alpha carbon carrying hydrogen. So this can show. This can also show. Next one. This is also an important point. This is called as 1,3 diketones. 1,3 diketones, we call it as a common name. Okay. They are also very important to show tautomerism. You can easily see that they will show tautomerism. Now the thing is, there are two different types of alpha carbons present here. One alpha carbon which is present between the two ketones, which is this one. It is alpha to this person also, it is alpha to this person also. And another alpha is the one which is present outside the two ketones, which is this alpha, corner alpha and middle alpha. corner alpha and middle alpha. Always remember to take out proton always from the middle alpha. Okay, this middle alpha carbon, we call it as active methylene group. Active methylene group. Very important case, please remember. Active methylene group. Whenever there is a double bond O here, CH2 here, double bond O here, anything could be present here. This particular group is called as active methylene group. Active methylene group. Okay, and the hydrogen on active methylene group is highly acidic, carries highly acidic proton. Okay, once you study about resonance effect and inductive effect, you will see that whenever this acts as a acid, it loses a H plus. If it loses a H plus, it will become a conjugate base which have a minus charge here. So this conjugate base is highly stabilized by resonance. This side also it can go resonance minus nothing pi. This side also it can go resonance minus nothing pi. Hi Vani Somnath, sorry. So, active methylene group, the CH2 group present between two electron withdrawing group is highly acidic in nature. So, always show tautomerism from here. Always show tautomerism from here, never from the outside. So, its enolic form is going to look like this. Let's say I'm showing enolization on the right hand side group. So, this alpha hydrogen has shifted to this oxygen like this. Like this. Okay. The center hydrogen, I've just taken it from here and I've done sigma become pi, pi become minus, minus take the H plus. This becomes the enol form. Now don't try to make both as enols because that will not happen. As soon as one of them you have made enol, then hydrogen bonding will start. So this C double bond O starts hydrogen bonding with this hydrogen OH group, and this intramolecular hydrogen bonding makes it a stable enol form. This enol form is also stable. Not as stable as keto, but still stable. So if the ratio initially was 99:1, now it almost reaches to like 8:92, like that. This is 92%, this is like 8% around. Exact value I'm not telling, but in beta diketones, you will see that the ratio, which was initially in normal ketones, it was 99% ketone, only 1%, 99% ketone and 1% enol was there. Now it is not that, it is almost 92%, it is almost 8%. So actually it has shifted, it has made the enol stable. Enol is stabilized by hydrogen bonding. Enol is stable due to intramolecular hydrogen bonding. So it almost reaches to 8% and this is almost 92%. Still keto is more stable, but as compared to previous cases, now keto has decreased a bit, enol has increased a bit. So in a normal ketones like acetone, keto 99, enol 1%, less than 1%. Then cases like this, beta diketones, where it reaches to 92 and 8. And then in enol cases where the aromaticity is reached, it can also go to 0 and 100, like in the case of phenol. So 3 cases I have told you basically where you can remember these ratios. Rest you can leave it. Ratio is not much important in the other compounds. Is it clear up to here, yes or no? Okay, so this is about keto-enol tautomerism, and different forms of keto-enol tautomerism I have shown you. So question can come like this. Arrange in increasing order of extent of enolization. Arrange in increasing order of extent of enolization. This one, this one, and this one. Let's say these are A, B, C. Increasing order of enolization means who will have more enol content. Okay, who will have more enol content. So this is a normal ketone. There is nothing special about him. This is a normal ketone. This ketone is not very good because its enol will be very, very good. Its enol will be phenol, which is aromatic in nature. So B will have the maximum enolization. B will have the maximum enolization, almost 100% enolization. Then A versus C, I told you that C ke enol mein there is hydrogen bonding. Because of hydrogen bonding, C will also enolize to a good extent. And A will enolize only marginally, only around 1%. So in the A, enol content will be 1%. In the B, enol content will be 100% almost. In the C, enol content will be almost 8%. These three you should remember. Tautomerism as a topic, not much there in the NCERT, but simple questions are getting asked from tautomerism. Okay, can be asked to you from tautomerism. This is about tautomerism. This is all about tautomerism. So what we have discussed is, what are the conditions to show tautomerism? What are the conditions to show tautomerism? Then what are the exceptions in tautomerism, which is alpha bridgehead carbon exception. And also we have seen the enolization extent in few important ketones. And I have also showed you the pentard shift when the alpha and beta are sp2, pentard shift can happen. And I have also shown you the example of other triad systems like nitro-acynitro and nitroso-oxime type of tautomers. Okay, so please revise up to here quickly. Then I will tell you few formulas to find total number of stereoisomers. And few examples we'll see. This is all about isomerism. I have discussed the complete isomerism part. Okay, I have discussed the complete isomerism part. Now coming back to stereoisomerism. Those who have not watched the yesterday's video, please watch it. Yesterday, day before yesterday, 2 videos we have done geometrical and optical isomerism. Okay. So in that stereoisomerism, just one thing was remaining, which I will tell you now. To calculate total stereoisomers. In a given compound. How many stereoisomers are possible? How to check? For this, 3 formulas will come beta. First thing you check whether the compound is asymmetrical or symmetrical. If the compound is asymmetrical, okay, asymmetrical compound means in keto-enol form, presence of which type of hydrogen is must? Acidic hydrogen, Niharika. Acidic hydrogen. Who is the acidic hydrogen? Either alpha hydrogen is acidic, Niharika. Alpha is acidic hydrogen, or gamma. If alpha and beta are sp2, then you can check gamma. You leave the gamma part. Alpha hydrogen presence is must. Alpha hydrogen is acidic in nature. So that is the condition to have acidic alpha hydrogen. Okay, acidic alpha hydrogen on a sp3 carbon. So hydrogen which is on sp3 carbon only can be acidic. sp2 and sp carbon hydrogens are not acidic in this case. Okay. So asymmetrical compound, if the molecule is asymmetrical, then total stereoisomers are going to be 2 to the power n. Like I told you in the geometrical isomerism, 2 to the power n. So, where n is what? N is number of stereocenters. N is number of stereocenters. What were stereocenters, beta? Stereocenters were either the chiral carbons or the C double bond C groups which were showing GI. Now I'm not considering separately GI, separately optical isomers. No, I'm talking about total stereoisomers. Total stereoisomers. So total stereoisomers will be 2 to the power n, where n is chiral carbons plus stereogenic pi bonds. See the example, everybody. See the example. Niharika, see here. If I look at this molecule, Niharika, okay, this particular molecule looks asymmetrical. Looks asymmetrical. I can't cut it into two equal halves. Now, how many stereocenters are there? See beta, this pi bond can act like a stereocenter. Yes, because it can show cis trans. And this carbon is a chiral carbon. So this chiral carbon is also a stereocenter. This chiral carbon is also a stereocenter. Okay. So this is a stereocenter and this is also a stereocenter. So n value is 2. So total stereoisomers are going to be 2 to the power 2, which is 4 isomers will be there. This particular compound will have 4 isomers. How 4 isomers? How will you check their configuration? See beta. This pi bond can be trans. Okay. This carbon can have R configuration. So trans and R is one possibility. Trans and R. It is obviously optically active because there is only one chiral carbon and it is optically active. So if you have a trans R, if I put a mirror next to it, a trans will remain trans only after putting a mirror. No. How trans will become cis? But R will become S. So if this is trans R, let's say, if this is trans R, let's say, this is trans R, let's say. I am not checking it is R or S, that you can check yourself. If I put a mirror beta here, how will the mirror image look like? It will look like this. Correct. So if this is trans R, this will become trans S, or vice versa. It may be trans S, this may be trans R. Okay. So this is the one. If I make it a cis can have a R configuration here. This configuration cis, this configuration R. Put a mirror, it will become cis S. Cis S. Okay. This happens when the molecule is asymmetrical, 2 to the power n. Simple. Simple. 2 to the power n. 2 to the power n. Possibilities are going to be there. Okay, sir. Can you give one more example? Yes, this was the first example. You take one more example. Example number 2. This is example number 2. In this example number 2, beta, it is also a symmetrical molecule because I can't cut it into two equal halves. It's a 2-bromo-3-chloro-butane. 2-bromo-3-chloro-butane. So I can't cut into two equal half. I have two chiral carbon. This is chiral carbon. This is chiral carbon. So cis transfer is not possible here. So possibilities are RR, RS, SR, SS. Four options will come. So here also total stereo will be 2 to the power 2, which is going to be 4. Those 4 are going to be 2R, 3R. Put mirror 2S, 3S. 2R, 3S. Put a mirror 2S, 3R. Okay. Whenever you put a mirror, always R become S. So these two are enantiomers to each other. These two are also enantiomers to each other. So RR and SS are enantiomer, RS and SR are enantiomers, RR and RS will be diastereomer. Okay, so this is how we can check. If you want, I can draw them. You can just see here. Carbon number 1, carbon number 2, carbon number 3, carbon number 4. Let's say this is the first compound I am drawing. Obviously, it is optically active. I cannot see any plane of symmetry. I'll draw its mirror image. I'll draw its mirror image where Br and Cl go to left side. This is mirror image. Okay, so these two are enantiomers. Now I'll keep Br and Cl on the different sides. So one possibility is to keep Br on right, Cl on left, and then its mirror image, which will be Br on left and Cl on right. So these are the four possibilities which are there. Which one is which, you can check yourself. Which one is 2R, 3R, then its mirror will be 2S, 3S, and so on. All four are optically active. All four are optically active. Okay, so whenever molecule will be asymmetrical, means obviously all will be optically active. 2 to the power n, all optically active. 2 to the power n, all optically active. Because when molecule is asymmetrical, there is no way that you are going to cut it into 2 equal half ever. Okay, so this is the way to find total number of stereoisomers for asymmetrical molecule. Now, what if the molecule becomes symmetrical? Or you can do one more example. Can you tell me for this one, how many, Niharika, how many optically active isomers for this compound? How many optically active isomer for this compound? I'll give 3 minutes for you to solve. You can tell me how many optical isomers are present for this compound. And for glucose also I'm asking. Tell me for glucose also. How many total stereoisomers are possible for open chain glucose? Open chain glucose. You know, glucose can have a closed chain structure also, but this is the open chain structure that we are drawing. Glucose 16. Okay, good. So glucose has how many chiral carbon? This carbon is chiral 1, 2, 3, 4. 4 chiral carbons are there. So 2 ki power 4, which is 16. That is correct. What about for this one? For this one, how many stereocenters? See, this carbon is a chiral carbon, one stereocenter. This pi bond can show cis trans, another stereocenter. This carbon is also chiral, beta. This carbon is attached to one hydrogen, one different group, one different group, one different group. So this is also chiral. And this carbon is also chiral here. 1, 2, 3, 4. So here also 2 to the power 4, 16 isomers are possible. For this compound also 16 will be possible. This is the chiral carbon, RS possible here. This is a cis trans possible here. Here also RS will be possible. It's a chiral carbon, as you can see. And this is also a chiral carbon. So 4 chiral here, 4 stereocenters here, 4 here. Now comes, if the molecule is symmetrical, case 2. If molecule is symmetrical, and it has even number of stereocenters. Even number of stereocenters. Symmetrical with even number of stereocenters means 2 stereocenters are there or 4 are there. Then apply the formula for total stereoisomers. As 2 to the power n minus 1. 2 to the power n minus 1 will be optically active, plus 2 to the power n by 2 minus 1 will be optically inactive. Means they will be mesocompound because molecule is symmetrical. I showed you in the last class, if chiral carbons are present, still there can be optical inactivity because of mesocompound. So the formula will become 2 to the power n minus 1 active and 2 to the power n by 2 minus 1 inactive. Inactive means mesocompounds. Okay, so this is the way to check. For example, one question which came in NEET 25 only, where you were drawing the cyclic ethers of C4H8O. One of the cyclic ether was coming out to be like this. This is a cyclic ether. But I can see that this is a symmetrical compound. I have a possibility of cutting it into 2 equal halves. So there is this chiral carbon. There is this chiral carbon. 2 carbons are chiral here. This carbon is attached to a methyl, a hydrogen, a C and a O. This carbon is attached to a methyl, a hydrogen, a C and a O. 2 chiral carbons are there. So N is equal to 2. But molecule is symmetrical. So here total stereoisomers are coming out to be 2 to the power 2 minus 1 plus 2 to the power 2 by 2 minus 1. See carefully. 2 to the power 2 minus 1, which is 2 ki power 1, 2 active plus 1 inactive. 2 to the power 1 minus 1, 2 ki power 0. 2 to the power 0. So here we got 2 ki power 1 plus 2 ki power 0, which is 2 plus 1, which is 3. 3 isomers are possible here. 3 isomers are possible. Now, how can I say 3 isomers? You can see here, everybody. Can it show cis-trans isomerism? Answer is yes. It can show cis-trans because we know that a ring acts as a restricted rotation center. So let's draw cis-trans first. Cis will look like this. CH3 coming out of the board, hydrogen behind the board, CH3 coming out of the board, and H behind the board. This is cis isomer of this compound. Then how the trans will look like? Trans will look like this. one methyl coming out of the board, one methyl behind the board. Like this. Okay, cis and trans, cis and trans. Now, if I look at cis, am I able to cut it into two equal halves? The cis part, yes sir, I can cut it like this. So cis is a optically inactive compound. It is a meso compound. So one meso compound, which is this. This is meso. This is cis. Am I able to cut trans into two equal half? Answer is no, sir. Trans does not have a plane of symmetry. So trans will have two possibilities. Trans dextrorotatory, put a mirror. Trans levorotatory. Trans dextrorotatory and trans levorotatory. This is the one. If I put a mirror, then this hydrogen will come forward. This methyl behind the board. And this carbon will shift here. So this methyl forward, this hydrogen backside of the board. So trans can be of two types, trans dextrorotatory and trans levorotatory. So two transes and one cis. Two active, one inactive. So total three isomers will be there. So these two are active. So total three. Three stereoisomers. Is it clear, Niharika? Can I think that it is clear to you? Same works for the tartaric acid I told you in the last class. Tartaric acid was D-tartaric acid, L-tartaric acid and mesotartaric acid. In the same way was for the tartaric acid. Same way there was tartaric acid. Tartaric acid was COOH, CHOH, CHOH, COOH. So this is also symmetrical molecule and this also has two chiral carbon. So what is the molecular formula for a stereogenic center alkene with the smallest molecular weight? With the smallest molecular weight. Now this particular question, Niharika, there are 2-3 ways to do it. First of all, they should mention that whether a hydrogen can be made deuterium, tritium or not. If they say hydrogen can be made deuterium, tritium, then you can draw very small one, thinking like this. These two groups should be different. Keep one hydrogen here, one hydrogen here. You can keep one deuterium here, one deuterium here. It can show cis trans. Okay. What is the molecular formula for the stereogenic center alkane, you are asking? Okay, alkane. Alkane you are asking. So you are trying to make this carbon as chiral carbon. So one to hydrogen I can keep. One deuterium, one tritium, one methyl I can keep. This is the minimum one you can get. This is the minimum one you can get. But thinking that there is no deuterium or tritium allowed, then in that case, you can go for one carbon methyl, other you can keep a ethyl, other you can keep a propyl. Okay, there is no other way possible. So one methyl will come, one this will come, and one propyl has to come. There is no other way to think of this one. So propyl, ethyl, methyl and a hydrogen. Okay, so this will be the possibility. 1, 2, 3, 4, 5, 6, 7. With the 7 carbon also you are able to get. Keep one hydrogen, keep one methyl, keep one ethyl and keep one propyl. To keep the mass minimum, 7 carbons you are able to get. But if they allow you to keep deuterium and tritium, then I told you within 2 carbons also you are able to get. Within 2 carbons also you are able to get. Okay. Since alkane is written, I can't think of keeping a vinyl group here. Otherwise, I would have done this. 1 hydrogen, 1 methyl. If they just ask hydrocarbon, then you could keep a vinyl here. CH double bond CH2 and here C triple bond CH. Now this becomes even lesser mass. This has even lesser mass than this. So if they ask hydrocarbon with the lowest weight, I will make this one. Hydrocarbon with lowest mass to show optical isomerism. Okay. Or to have a chiral carbon to show chiral carbon. Then I will think of this one. This is the alkane to have a chiral carbon. C4H10 can be possible, sir. C4H10, no. Butane will not have any chiral carbon. This is one form of butane. This is another form of butane. So there is no chiral carbon in the butane. Answer is no. Okay. So at least 7 carbons are required. If what question you have asked, according to that 7 carbons are required. Before heptane, you cannot have the optical isomerism. Before heptane, you cannot have the optical isomerism because this is hexane. Hexane can become methyl pentane. Hexane can become dimethyl butane. No, not possible. So at least 7 are required. So answer is this, 7 carbon. Okay. Chalo. So I'll keep it till here. Tartaric acid also same case. 2 chiral carbons and symmetrical molecules. So 3 total structures will come. 3 total structures will come. Okay. Bye bye. Thank you everybody. Thank you for listening. I'll see you all in the tomorrow's class. Bye bye.